Alright, so as I discussed in an earlier video, there are two situations in which the system would have zero acceleration. And zero acceleration, or zero net force, is what we describe as being in equilibrium. We're going to learn later on in the semester a second condition for static equilibrium, but we're going to focus on the force one for now. So, as I said before, equilibrium means that the acceleration is equal to zero, which in turn means that the force net is equal to zero. Now, don't be confused. You can still have forces acting in the system, but it just means that the negative and positive forces are balancing each other out. So when you add them together, indicated by the word net, you end up with a value of zero. And the two conditions where you have this setup is if the system isn't in motion, so system not in motion, or the system is moving with constant velocity. Because remember, when velocity is constant, that means that the acceleration is zero. Because remember, acceleration is equal to change in velocity with respect to time. So if your final velocity and your initial velocity are the same value, when you subtract, you get zero. So sometimes in problems you'll be given velocities not for the sake of needing to use the velocity in the problem. The magnitude of the velocity is irrelevant. The word constant that comes before or after it, that's the important word, which tells you you're in the second scenario that I just discussed. So be careful when you thoroughly read a problem, whether you're given an acceleration or you're given a velocity. So make sure you're not plugging a velocity into an acceleration spot in our formulas. Alright, so we are now going to apply the concept of equilibrium and our problem-solving rules to solve our first problem. So we have a wire 1 which is fixed to a wall at one end with an angle between the negative x-axis and wire 1 being 55 degrees. So see, we have a wall, and then we have wire 1 coming down, and there's going to be a 55 degree angle in here. And then we have wire 2 which is attached to the other end of wire 1 and to the opposite wall, and there's going to be an angle of 30 degrees. So we have our other wire. So let's see. This is wire 1, this is wire 2, and this is an angle of 30 degrees. And then right here, there is a 50 kilogram mass attached. And we want to know what the tension is in wire 1 and wire 2. Alright, so going through our problem solving steps, step 1 is to pick an object to sum forces on. And it's not obvious in tension problems like this, but we want to sum forces on the junction point where all of our forces come together. So we're going to sum forces on this junction point. Now we need to identify the forces present in the system. So we're going to have a force due to tension 1, and that's going to act in the negative x but positive y direction. Because from this junction point here, the wire is going to pull it up towards the wall. The other item touching the junction point is wire 2. And that's going to exert a force due to tension as well, but this one's going to be positive x and positive y. Because from the junction point, the wire is going to pull up towards the wall, which is up in the first quadrant. And then the last item touching the junction point is going to be this weight hanging down here. And that's going to exert a force equal to the mass's weight. So we're going to have an FG there. That's going to be in the negative y direction since it's hanging vertically. Technically speaking, the strings themselves should have masses, but we ignore strings, wires, etc. as masses to make our problems a little bit easier. Alright, so now we need to draw a free body diagram. And when tension 1's like this, it's a little silly, but it allows us to then break down the forces into components. So we have force due to tension 1 up in our second quadrant, force due to tension 2 in the first quadrant, and then the weight of the mass hanging down here. And remember, we have to keep x's and y's separate, so force of tension 1 is going to have an x component to it and a y component to it. And so we'll force due to tension 2. Alright, so now we need to move on to step 4. So we first need to add together all the forces acting in the x directions, and being careful if the force acting in multiple directions, we're adding only the components for that direction. So in the x direction, we have a negative force of tension 1 in the x, and then we have force of tension 2 in the x, but this one's going to be positive because it points to the right. And that's going to sum to 0 because our system is at rest. So the x component of force of tension 1 is going to balance out the x component of tension 2. Alright, that tells us something useful, that the x components are equal to each other, but it doesn't tell us what the x components are. So let's go a little bit further and do our trig substitutions. So we're given the angle in here, which means that the x components are both adjacent, so we're going to use cosine. So we're going to replace force of tension 1, so that's the hypotenuse of the triangle, times the cosine. Let's see, 1 would be 55 degrees. And then we're going to take the hypotenuse of the triangle, so force of tension 2, times the cosine of 30 degrees in this case. Alright, so we're stuck because we have two unknowns. So let's go to the y direction. In the y direction, we have, force of tension 1 in the y, plus force of tension 2 in the y, minus the weight of that mass hanging there. And those are going to sum to 0, because once again the system is at rest. So the two y components of the tension is going to balance out the weight pulling down. Once again, we need to do a trig substitution, and this time the angles are both opposite to the side of interest, so we're going to use sine. So we're going to take the hypotenuse times the sine of 55 degrees plus the hypotenuse again of the other triangle times the sine of 30 degrees. And let's see, remember FG is equal to the mass times the acceleration due to gravity, or the gravitational field strength, however you want to think about it. So we're going to take the 50 kilogram mass here times 9.8 meters per second squared. Alright, now we still have two unknowns, but we have two equations now, so we can do an algebraic substitution to finish up this problem. Alright, so I've just rewritten the equations we ended with on the prior page. And I'm going to solve this first equation for force of tension 2. So force of tension 2 is going to equal force of tension 1 times the cosine of 55 degrees divided by the cosine of 30 degrees. And I'm going to sub that down here for force of tension 2. So that's going to give me force of tension 1 times the sine at 55 degrees plus force of tension 1 times cosine at 55 degrees divided by cosine of 30 degrees. And then don't forget there was still a sine of 30 multiplied over here. I always like to forget that. And then we have 50 kilograms times 9.8 meters per second squared. So you'll notice now that our only unknown is force of tension 1. Alright, so we end up with 0.819 force of tension 1 plus 0.331 force of tension 1. It's going to equal 490 newtons. So we can add our two terms together. Since these are the same variables, we can add our leading numbers together. and we end up with 1.15. Force of tension 1 equals 490 newtons, or that force of tension 1 is equal to 426 newtons. So we now have force of tension 1, which we can then plug in up here. So force of tension 2 is going to equal 426 newtons times the cosine of 55 degrees divided by the cosine of 30 degrees. So force of tension 2 is going to equal 282 newtons.